This is Chapter 11, Our Star, in the Astronomy 100 course for Waubonsie. In the first section, we're going to take a closer look at the Sun. Our goals are, why does the Sun shine, and what is the Sun's structure? This is a great photograph of the Sun and some of its features in its inner and outer atmosphere. We're going to look at why the Sun shines. The first question people would ask was, is the Sun on fire? And of course it's not, or it wouldn't last as long as it has, with chemical energy being the fuel. Its estimated lifespan would only be about 10,000 years. Is it contracting? Is it burning fuel but at the same time getting smaller and smaller? The answer there is no as well. Its lifespan would only be about 25 million years based on gravitational potential energy being the force that burns or makes the Sun burn. So that's not it. What about nuclear energy? Well, in the form of nuclear fusion, that seems to be the way the Sun is producing energy. It uses the old principle of E equals mc squared, that being able to take nuclear potential energy in the form of mass and converting it to energy, our Sun has a lifespan of about 10 billion years. What we have to remember about the internal structure of the Sun is that there's a tremendous weight overlying the core, the innermost layers of the Sun. So that's going to compress those layers. Gravity is going to pull things in, of course, but the pressure of the Sun burning is going to generate pressure outward. So fortunately, we have an equilibrium between pressure and gravity that keeps the Sun at about the same size. We also have an energy balance. Heat is being radiated toward the surface after fusion occurs near the core, and then that radiation is escaping. So there's generally a radiative balance from the energy lost at the surface. The gravitational attraction or contraction inside provides energy that heats the core as the Sun first formed, and that contraction stopped when the fusion started, replacing the energy, radiating it out into space. So again, there was initially some contraction of the Sun, but only until the heat of radiation balanced it out. So let's look at the Sun's structure, both internally and around the surface. These are some common factors of our Sun. About 109 diameters, Earth diameters, would fit across the surface of the Sun. About 300,000 Earths would fit inside the Sun. And the luminosity is expressed in watts. A 100-watt light bulb might be a good comparison, which is 1 times 10 to the 2 watts. So the Sun has much, much more luminosity, obviously. The Sun has what's called solar wind, or generates solar wind. As the Sun generates energy, eventually it coming to the surface, it pushes charged particles outward from the surface. There's also the corona, which is the outermost layer of the solar atmosphere. Its temperature is roughly 1 million kelvins, which is very, very hot. But fortunately, the density of that part of the atmosphere is very, very low. So even a spacecraft flying through the corona would not really sense that tremendous amount of heat. And there's the inner atmosphere, which is called the chromosphere. That's the middle layer of the solar atmosphere, and that runs somewhere between 10,000 and 100,000 kelvins. So it's a cooler layer. And then there's the photosphere, which we see as the visible surface of the Sun, and that's approximately 6,000 Kelvin. So that temperature gives us a visible wavelength of kind of a whitish yellow color for the surface of the Sun. Inside the first layer of the sun is what's called the convection zone, where energy is transported upward by rising hot gases. Below that is something called the radiation zone, where energy is transported upward by photons. Those photons are being generated deep within the core of the sun. And finally, here's the core, where the energy generated is by nuclear fusion, not by nuclear fission, but nuclear fusion, and the internal temperature is said to be about 15 million Kelvin. So what have we learned? Well, why does the sun shine? Well, there's chemical and gravitational energy sources that could not explain how the sun could sustain its luminosity for more than about 25 million years. So we've found that the sun shines steadily because nuclear fusion in the core maintains gravitational equilibrium between pressure and gravity, and energy balance between thermal energy released in the core and radiative energy lost from the sun's surface, keeps things pretty much in balance. The sun's structure, as we've already gone through, starting from the inside going out, we start with the core, then the radiation zone, the convection zone, the photosphere, which we can see as the surface of the sun, the inner atmosphere, which is called the chromosphere, and finally the outer atmosphere, called the corona. So in section 11.2, we're going to look at nuclear fusion in the sun and try to keep it as simple as possible. How does nuclear fusion occur in the sun? How does the energy from fusion get out of the sun? And how do we know what's happening inside the sun? Well, here's the difference between the two basic nuclear processes. Nuclear fission on the left is where a very heavy atom, such as uranium, is split into two somewhat smaller atoms or nuclei. So the process of fission does release energy, and of course we've harnessed it in a couple of different ways. We've been able to take the heat generated by fission and take that heat, make water boil, take the steam, run it through a turbine, and generate electricity. That's what our nuclear power plants are doing today. Unfortunately, nuclear fission can also be used to make nuclear weapons, and the results of that could be seen as bombs were dropped over Hiroshima and Nagasaki to end World War II. Fusion, on the other hand, is where two very small or light nuclei combine to form a heavier atom. In this case, we're taking hydrogen and fusing it to form helium. So fission brings big nuclei together, it splits them into smaller pieces, and fusion takes small nuclei and sticks them together to make a bigger one. So nuclear fusion is just the opposite of nuclear fission. But as we know, nuclear fusion produces much, much more energy in that conversion process than nuclear fission does. So high temperatures enable nuclear fission to happen in the core. High temperatures mean particles move faster. And at 15 million Kelvin, they're moving very, very fast. So fast that it's possible for the nuclei of hydrogen atoms to fuse together. There are several forces in nature. One of them is called the strong force. And that's the type of force that brings these nuclei together. Gravity, electromagnetism, all the other forces don't have as much power as the strong force when these nuclei are very, very close together. So here's what it looks like in very simple form. Taking 4 hydrogen nuclei, 4 protons, combining them to give us 2 protons, 2 neutrons, that's helium. But the small amount of mass difference in that conversion is converted to energy, and that's the energy that radiates outward from the sun eventually. This is a more detailed description of nuclear fusion, where we get where we put 4 protons in, and out of that we get 1 helium nucleus, 2 gamma rays, 2 positrons, and 2 neutrinos. The total mass is 0.7% lower than the original mass. As I said before, that's the mass that gives us the energy that we have the sun radiating toward us. Fortunately, the sun acts as its own thermostat. So between the reactions that are occurring in nuclear fusion and the pressure pushing that energy outward, the gravitational attraction pulling it all in, the temperature of the sun remains fairly constant. So how does the energy from fusion get out of the sun? Well, as you can see by this red line, it's a very random pattern for this energy to move eventually out toward the surface. But it does. It may take many, many years, but eventually it does reach the surface. We see the results of that movement in what's called convection cells. These whitish splotches that you see in the bottom right are where hot gas is rising toward the surface, and the darker areas is where cooler gas is sinking. The bright blobs are where the gas does reach the surface. So how do we know what's happening inside the sun? This is kind of interesting because obviously we can't drill down into the sun to find out what's happening here, but based on these three things, we have a pretty good idea. Making mathematical models of the sun, observing solar vibrations, and observing something called solar neutrinos. These patterns of vibration on the surface tell us about what the sun is like inside. And what you see here is the result of measuring the sun with the Doppler effect. As you recall, something moving away from you is redshifted, something moving toward you is blue shifted. Well, the area on the left is redshifting, and on the right is blue shifting. And the stippling pattern that you see in the sun are minor vibrations in the sun. This graph really isn't in the book, but I thought it would be interesting to show. This data on solar vibrations agrees with the mathematical models of what the solar interior should be like. So there's definitely a good correlation between what we think is happening and what is probably happening in the sun. The neutrinos that are created during fusion fly directly through the sun. They are totally unhampered by matter. And observations of these neutrinos can tell us what's happening in the core. As the book describes, neutrinos are very, very fast, very energetic, and pretty much pass through anything, including us and the Earth. So, in order to block out any other particles that might interfere with our measurements, early searches for solar neutrinos failed to find the predicted number that should be produced. So, more recent observations find the right number of neutrinos, but some have actually changed in form. This big ball sitting deep inside a mine is something that's being used to detect neutrinos. Other forms of radiation and particles would be blocked by the Earth above it, but neutrinos, being able to pass right through the Earth, could actually be detected by this device. So what have we learned? Well, how does nuclear fusion occur in the sun? The core's extreme temperature and density are just right for nuclear fusion of hydrogen to helium through what's called the proton-proton chain. And gravitational equilibrium and energy balance act together as a thermostat to regulate the core temperature because the fusion rate is very sensitive to temperature. Obviously, if this equilibrium wasn't there, it would be possible for the sun's core to overheat, get too hot, or to possibly expand and get too cool, where fusion would then stop. How does the energy from fusion get out of the sun? Well, randomly bouncing photons carry it through the radiation zone, and the rising of hot plasma carries energy through the convection zone to the photosphere. So those layers are critical in transporting the energy from the core outward to the photosphere. How do we know what's happening inside the sun? Well, mathematical models agree with observations of solar vibrations, and we have solar neutrinos that pretty much confirm this is one part of what the energy balance is for the sun. So this is 11.3, the Sun-Earth connection. What causes solar activity, and how does solar activity vary with time? This is an X-ray photo from a NASA satellite that shows hot gas trapped within magnetic field lines on the surface of the sun. These are all different phenomena that are occurring on the sun's surface. Sunspots, which you've probably heard of before, solar flares, and solar prominences. And they all seem to be related to the magnetic field the sun produces. As you can see here in a very, very good close-up, these are sunspots. Those are the cooler spots. They're cooler than the other parts of the sun's surface. If the sun's surface is 55 to 5800 Kelvin, sunspots are down around 4000 Kelvin, so they're definitely cooler. And they're regions with very strong magnetic fields. These are the magnetic field lines that you'd be able to detect with something like a compass. These are generated by the Earth as it rotates and it has a metallic core. The sun does the same thing. It produces a very, very strong magnetic field. So charged particles can actually move along these magnetic fields or disturbances in the magnetic field. And these loops of bright gas often connect pairs of sunspots. So the cool spots are disturbances in the magnetic field, and particles can fly along those magnetic field lines like you see in the photo. Magnetic activity causes solar flares, and these solar flares can send bursts of X-rays and other charged particles into space. And of course, if the solar flare occurs in the direction of Earth, we could possibly have some strange things happening here. We also have magnetic activity causing solar prominences that erupt high above the sun's surface. So again, the magnetic field being disturbed, being twisted, can cause these large eruptions on the sun's surface. Here's a good picture showing the differences in the corona, which appears bright in X-ray photos in places where magnetic fields trap hot gas. And of course, near the pole there, we see a dark spot where the corona is not producing much, if any, radiation. We have these other events called coronal mass ejections, which send very, very large bursts of charged particles out through the solar system. And again, this can happen in any direction, in any orientation, but if they happen to be sent out our way as we're orbiting the sun, it causes some problems. Those problems can disrupt electrical power grids, disrupt communication satellites, cause auroras. There's lots of things that these solar particles can do in and around the Earth. So how does solar activity vary with time? Well, this is one of the graphs that was in the book, and as you can see, the percentage of sun's surface covered by sunspots varies at a pretty regular rate. As it turns out, roughly 11 years. Same graph is on the top, but what's interesting is the graph at the bottom, which shows how sunspot location varies through the years as well. As you can see, there are sunspots which are occurring 30 degrees north and 30 degrees south, and then they generally migrate toward the equator as the sunspot activity goes up. And again, it's at a fairly regular pace. The sunspot cycle has something to do with the winding and twisting of the sun's magnetic field. And apparently this twisting and bending and eventually breaking of the magnetic field has this regularity, this 11-year cycle. So what have we learned? Well, what causes solar activity? It's the stretching and the twisting of the magnetic field lines near the sun's surface causing solar activity. And bursts of charged particles from the sun can disrupt communication satellites and electrical power generation. So there's a definite correlation between what the sun is doing in terms of magnetic field lines and those lines being disturbed or twisted, and what we sense here within a matter of only a couple of days after these events occur. So how does solar activity vary with time? There seems to be a rise and fall of these activities in an 11-year cycle.